The Ilyushin Il-28 sits on tires that look like they were stolen from heavy agricultural machinery. To an observer accustomed to the sleek, high-pressure tires of modern combat aircraft, the landing gear of this Soviet bomber appears almost comically oversized, requiring tire pressures so low that Western aeronautical engineers of the late 1940s would have considered it a structural liability. But this was an intentional, uncompromising choice. While the United States Air Force was pouring millions of cubic yards of concrete across Europe and North America to support delicate, heavy, long-range bombers with high-pressure landing gear, the Soviet Union chose a different path. They built a jet bomber that could take off from a frozen potato field. The Ilyushin Il-28, known to NATO as the Beagle, is an aircraft of extreme contradictions. It possesses the aerodynamic profile of a slightly flattened cigar with straight, unswept wings, giving it the appearance of a World War II relic that somehow had jet engines awkwardly grafted onto its frame. Yet, it became one of the most widely produced, widely exported, and longest-serving jet bombers in human history. It was designed to deliver early atomic weapons, yet it was engineered to be maintained by conscript mechanics wielding the aviation equivalent of a tractor wrench. This aircraft embodies the central paradox of early Soviet jet doctrine. How do you deploy a high-speed, technologically advanced jet strike force in an environment where your own military planners assume all paved infrastructure will be cratered into oblivion within the first 3 hours of a conflict? The Il-28 was the answer. It did not just tolerate rough conditions, it was designed around the premise that the end of the world would not feature pristine runways. But building a high-speed jet that could land in the mud required severe compromises that would shape its combat record, dictate its tactical limitations, and subject its crew to extreme physical demands. If you enjoy detailed deep dives into military engineering and strategy, subscribe to the channel. I've got a lot more planned. To understand why the Il-28 looks and performs the way it does, we have to examine the geopolitical and tactical realities of the late 1940s. The Soviet Union had just emerged from a devastating war where tactical air power, heavily armored ground attack aircraft, and light bombers operating from temporary dirt strips right behind the front lines had proven decisive. Soviet frontal aviation doctrine demanded aircraft that could stay close to the rapidly advancing or retreating ground forces. When jet propulsion arrived, the mandate did not change. The High Command demanded a bomber that could fly fast enough to evade jet interceptors, carry a massive bomb load, and do it all from unpaved, unprepared airstrips carved out of the forest or the steppe. The heart of the Il-28's design, and the source of its first major engineering compromise, was its propulsion system. In the immediate post-war years, Soviet jet engine development was lagging behind the West. They possessed captured German axial flow engines, like the Jumo 004, but these were notoriously unreliable, offering dismal thrust and a lifespan measured in mere hours. The solution came through an unexpected avenue: the British government. In a move that still baffles historians and infuriates Cold War strategists, the British allowed the export of the Rolls-Royce Nene centrifugal flow turbojet to the Soviet Union. The brilliant Soviet engine designer Vladimir Klimov immediately reverse-engineered the Nene, creating the Klimov VK-1. It was powerful, rugged, and reliable. But centrifugal flow engines come with a massive physical penalty. Unlike axial flow engines, which compress air in a straight line through multiple stages of fan blades, allowing for a slender profile, a centrifugal engine compresses air by spinning it outward using an impeller. This requires the engine to have a massive diameter. When the Ilyushin Design Bureau went to mount 2 VK-1 engines on their new bomber, they realized the engines were simply too fat to bury inside the fuselage without sacrificing the bomb bay or the fuel tanks. The only solution was to mount them on the wings. But the enormous girth of the VK-1 meant that the engine nacelles were gigantic, creating immense drag. The nacelles on the Il-28 actually protrude far forward of the wing leading edge and extend entirely past the trailing edge. From an aerodynamic standpoint, they are massive speed brakes. This engine placement solved the immediate need for thrust, but it created a new aerodynamic challenge. The massive nacelles disrupted airflow over the wing to such a degree that utilizing a highly swept wing, the standard solution for achieving high speeds in early jets, became incredibly complicated. Swept wings were notorious for vicious stall characteristics and poor low-speed handling. If you combined the unpredictable low-speed aerodynamics of early swept wings with the massive airflow disruption of those fat VK-1 nacelles, you would get an aircraft that was lethal to fly on approach. And remember the primary requirement: this aircraft had to land on short, muddy, rough strips. A high landing speed was entirely unacceptable. Therefore, Ilyushin made a deliberate, controversial choice. They abandoned the swept wing entirely. The Il-28 features a completely straight, unswept wing. This provided excellent stable lift at low speeds. It allowed the incorporation of massive, trailing-edge flaps, which gave the bomber a stall speed slow enough to approach a short dirt strip with confidence. The straight wing made the aircraft docile, predictable, and remarkably forgiving for the pilot. But aviation design is a ledger of debts, and the straight wing demanded a harsh payment in top speed. As an aircraft approaches the speed of sound, the air flowing over a straight wing accelerates locally to supersonic speeds, creating massive drag, shock waves, and a loss of control known as Mach tuck. The Il-28 hits a rigid aerodynamic wall at approximately Mach 0.79. It simply cannot go any faster in level flight without shaking itself apart or diving into the ground. This strict speed limit generated the next nested problem. In 1948, Mach 0.79 was fast enough to leave any piston engine fighter in the dust. But the Il-28 was expected to serve into the 1950s, an era when swept-wing jet interceptors like the American F-86 Sabre and the Soviets' own MiG-15 were taking to the skies. These fighters could easily break Mach 0.85 and would have no trouble catching the Beagle. The straight-wing compromise meant the bomber was fundamentally vulnerable. It could not rely on speed alone for survival. Because it could not outrun interceptors, it had to fight back. And this requirement led to one of the most distinctive and grueling aspects of the Il-28, the tail gunner's station. Unlike Western bombers that were increasingly relying on automated defense systems or stripping guns entirely to save weight, the Soviets installed a massive stinger on the back of the Il-28. The Il-K6 tail turret was a formidable piece of engineering, housing twin Nudelman Richter NR-23 cannons. These 23mm weapons fired massive, explosive projectiles at a high cyclic rate. The turret was hydraulically driven and eventually directed by a radar system mounted in a radome just above the guns, allowing the gunner to track and engage targets in low visibility or at night. To operate this heavy weaponry, a human gunner had to be stationed at the extreme rear of the aircraft. But because the Il-28 was designed to operate at altitudes up to 40,000 feet, the crew required a pressurized environment. Rather than pressurize the entire length of the fuselage, which would have added immense weight and complicated the design of the cavernous, unpressurized bomb bay in the center of the aircraft, Ilyushin engineers split the crew. The pilot and the navigator sat in a pressurized forward cabin. The tail gunner was sealed inside his own tiny, isolated, pressurized capsule at the very back of the aircraft. Operating in that rear capsule was a punishing physical and psychological ordeal. The gunner was entirely cut off from the rest of the crew, connected only by an intercom system. If the intercom failed, he was completely alone, flying backward at 500 miles per hour. Furthermore, the position of the capsule at the extreme rear meant that any turbulence or any yawing motion induced by the pilot up front was violently amplified at the tail. The tail of an aircraft acts like the tip of a whip. During evasive maneuvers, the gunner was subjected to nauseating lateral G-forces. Additionally, the physical recoil of the twin 23mm cannons was staggering. When the gunner opened fire, the recoil forces were transmitted directly into the airframe structure surrounding his small cabin, filling the space with concussive shock waves, the acrid smell of cordite that invariably leaked past seals, and deafening noise. Yet this isolated, uncomfortable crewman was the primary reason intercepting an Il-28 was considered highly dangerous. The twin 23mm cannons provided a lethal cone of defensive fire that forced enemy fighters to break off their standard stern approach attacks and attempt much more difficult deflection shots from the side. The addition of this heavy tail turret solved the vulnerability problem caused by the straight wing, but it introduced yet another engineering challenge: weight distribution. Hanging hundreds of pounds of cannons, ammunition, armor plating, radar equipment, and a human being at the absolute rear of the aircraft severely shifted the center of gravity backward. To balance the aircraft, heavy equipment had to be pushed as far forward as possible. This brings us to the front of the aircraft, which is dominated by a heavily glazed greenhouse nose. This was the domain of the Navigator Bombardier. Inside this glass enclosure, the Navigator operated the OPB-5 bomb sight and the PSBNM navigation and bombing radar housed in a Chinra dome beneath his feet. The Navigator's role was critical. He was responsible for finding the target, plotting the course, and actually releasing the ordnance. But his position, suspended in a glass bubble ahead of the front landing gear, came with severe operational hazards. In an emergency, escaping the Il-28 was a complex affair. The pilot, sitting in a fighter-style cockpit under a bubble canopy, had a conventional upward-firing ejection seat. But the Navigator could not eject upward. His trajectory would take him straight through the pilot's cockpit or the solid roof structure. Therefore, the Navigator was provided with a downward-firing ejection seat. This mechanism required the Navigator to pull a handle that jettisoned a lower hatch and fired him out of the bottom of the aircraft. At high altitudes, this was effective. But during the critical phases of takeoff and landing, when a large percentage of aviation accidents occur, a downward-firing ejection seat was virtually useless, if not outright fatal. If an engine failed on takeoff and the aircraft was only a few hundred feet off the ground, the Navigator had no viable means of escape. He simply had to brace for impact. The tail gunner faced a similar hazard, utilizing a bottom hatch that dropped him away from the aircraft, avoiding the massive horizontal stabilizers above him, but rendering low-altitude escapes equally impossible. We've seen how the need for rough field performance forced a straight wing, which limited speed, which required a heavy tailgun, which necessitated splitting the crew and complicating the ejection system. But how exactly did the Il-28 achieve that phenomenal rough field capability? The answer lies in the pneumatic system and those massive agricultural-looking tires. So, after seeing how it actually performed, do you think the design approach was worth it? Let me know in the comments. In Western aviation, hydraulic fluid is the lifeblood of an aircraft. It operates the landing gear, the flaps, the bomb bay doors, and the brakes. Hydraulics are precise, powerful, and responsive. However, hydraulic systems have drawbacks that Soviet engineers were acutely aware of. Hydraulic fluid is highly flammable. A single bullet severing a line could atomize the fluid, turning the interior of the aircraft into a fuel-air bomb waiting for a spark. Furthermore, in the extreme sub-zero temperatures of a Siberian winter, hydraulic fluid becomes sluggish, prone to freezing, and causes seals to crack and leak. Therefore, the Il-28 minimized hydraulics. Instead, it relied heavily on a high-pressure pneumatic system. Compressed air, stored in heavy steel bottles and constantly replenished by engine-driven compressors, was used to actuate the landing gear, open the bomb bay, and operate the brakes. Compressed air does not freeze in winter. If a pneumatic line is severed by enemy fire, it simply vents harmless air. It doesn't start a fire. It is a rugged, simplistic system perfectly suited for harsh environments. The cost of this ruggedness was a lack of precision. Pneumatic systems are notoriously difficult to modulate. Unlike hydraulic brakes, which a pilot can gently squeeze to apply smooth deceleration, pneumatic brakes tend to be highly aggressive. They are either on or off. Pilots had to carefully tap the brake levers on the control yoke, listening to the sharp hiss of compressed air, being careful not to lock the wheels and blow those massive tires. And the tires themselves were the ultimate expression of the end-of-the-world design philosophy. They were enormous, low-pressure flotation tires. The physical principle is simple. By increasing the surface area of the tire and lowering the internal pressure, you distribute the heavy weight of the bomber over a much larger footprint. This prevents the tires from sinking into mud, snow, or soft dirt. It is exactly the same principle used by tracked vehicles or snowshoes. But physics always exacts a toll. Those massive wheels had to go somewhere when retracted. They were too large to fold flat into the thin, straight wings. The only option was to rotate them 90 degrees and pull them up into the engine nacelles. But even the massive VK1 nacelles didn't have enough room for the main gear, so the wheels actually had to retract inward into the fuselage. This required enormous wheel wells carved out of the lower fuselage. The space taken up by these gaping cavities was space that could not be used for fuel tanks. As a result, the internal fuel capacity of the Il-28 was severely limited. To achieve any meaningful range, the bomber had to rely on large external drop tanks mounted on the wingtips. These drop tanks, while solving the range issue, added further aerodynamic drag and reduced the overall maneuverability of the aircraft. When you move from the engineering drawings to the operational reality of the flight line, the genius of these compromises becomes starkly apparent. The Il-28 was an absolute joy for ground maintenance crews. Because the aircraft sat relatively low to the ground on its trailing link suspension, and because the engines were mounted beneath the straight wings rather than buried in the fuselage, mechanics did not need specialized ladders or complex gantries to service the aircraft. The cowling of the VK-1 engines could be unlatched and swung open by a single mechanic standing on the ground, exposing the entire engine for maintenance. In a tactical scenario where ground support equipment might be destroyed or unavailable, this was a massive advantage. Crews could perform engine changes, reload the 23mm cannons, and winch bombs into the bay using rudimentary hand tools and physical labor. The aircraft could be refueled from standard trucks without specialized high-pressure pumping equipment. It was a frontline brawler designed to live in the dirt. From the pilot's perspective, the Il-28 was heavy but honest. It lacked hydraulic-boosted flight controls. The control column was connected to the elevators and ailerons via a complex series of push rods and cables. This meant the pilot felt the raw aerodynamic forces acting on the airframe. At high speeds, the controls became incredibly stiff, requiring significant physical strength to maneuver the aircraft. A combat pilot flying an evasive routing in an Il-28 was getting a severe physical workout. However, this mechanical directness, combined with the straight wing, made it an exceptionally stable bombing platform. In turbulent air, where a highly swept wing might Dutch roll or hunt for an aerodynamic center, the Beagle tracked straight and true. This stability was vital for the navigator attempting to line up a target on the crude glowing green screen of the PSBN-M radar scope. The aircraft's operational combat history perfectly reflects its rugged, contradictory nature. It rarely served in the strategic, high-altitude atomic role it was ostensibly built for. Instead, it was pushed to the tactical edges of the Cold War, serving in proxy conflicts where environmental conditions destroyed more sophisticated hardware. During the Suez Crisis of 1956, Egyptian Air Force 1 Il-28s became priority targets for British and French forces. The Western Allies recognized that while the Beagle was obsolescent in a European theater, its ability to carry heavy conventional bomb loads posed a massive threat to staging areas and naval assets. Most Egyptian Beagles were destroyed on the ground, caught out in the open precisely because they didn't require specialized protected bunkers to operate. In the late 1960s, during the Nigerian Civil War, the Nigerian Air Force operated Il-28s, flown by Egyptian and later Soviet mercenary pilots. They flew out of poorly maintained civil airstrips, operating in intense tropical heat and massive humidity. The environment would have crippled the delicate electronics and high-pressure landing gear of a Western tactical bomber within weeks. Yet the Beagle pounded out daily sorties, shrugging off the abysmal runway conditions, relying on its pneumatic systems and thick tires to absorb the punishment of potholed tarmac and laterite dirt. Similarly, in the skies over Yemen, the Il-28 operated from high-altitude, dusty strips where sand ingress was a constant threat. The rugged, simple centrifugal flow compressor of the VK-1 engines could ingest sand and debris that would have catastrophically shredded the finely tuned compressor blades of an axial flow engine. The engine might lose efficiency and run hot, but it kept running, allowing the crew to return home. The ultimate testament to the Il-28's underlying brilliance is not found in Soviet records, but in Chinese engineering. When the Sino-Soviet split severed technological ties between the two communist powers, the Chinese possessed a fleet of Il-28s, but lacked spare parts or replacement airframes. Rather than design a new aircraft from scratch, the Harbin Aircraft Manufacturing Corporation meticulously reverse-engineered the Beagle, producing it as the Harbin H-5. The Chinese engineers looked at the compromises Ilyushin had made and refined them. They realized the airframe was fundamentally sound, but they optimized the manufacturing process, reducing the number of structural components to make it cheaper to build. They modified the bomb bay to carry indigenous Chinese munitions. Most notably, they redesigned the tail gunner's turret, replacing the original ILK-6 unit with a design derived from the larger Tu-16 bomber, providing better visibility and slightly better ergonomics for the unfortunate gunner trapped in the rear. The H-5 clone kept the basic Beagle design flying well into the 1990s, operating from austere bases across China and being exported to North Korea and Romania. It is a profound irony of military aviation history that the Il-28, a bomber originally intended as a stopgap measure in the late 1940s, ended up far outlasting the aircraft designed to replace it. The supersonic swept-wing Yakovlev Yak-28 was supposed to render the Beagle obsolete. The Yak was fast, sleek, and carried advanced radar, but it was incredibly complex, dangerous to fly at low speeds, and entirely reliant on pristine, long concrete runways. When the geopolitical reality demanded aircraft that could reliably launch from secondary airstrips and deliver conventional weapons with minimal maintenance, the sophisticated supersonic replacements were grounded, while the aging, straight-winged Beagles and H-5s were towed out to the dirt strips, engines howling as they accelerated through the mud. This resolves the central mystery of the Ilyushin Il-28. It looked primitive because it refused to sacrifice operational availability for theoretical performance. In the sterile environment of an engineering drafting board, a swept-wing bomber with high-pressure tires and advanced hydraulics is superior. It flies faster, goes further, and carries more. But warfare does not happen on a drafting board. It happens in the mud, in freezing rain, on runways cratered by enemy action and hastily patched with steel matting and gravel. The designers of the Il-28 understood that an aircraft with a maximum speed of Mach 0.79 that is actually airborne is infinitely more useful than an aircraft with a maximum speed of Mach 1.5 that is stuck in a hangar waiting for specialized hydraulic fluid and 2 miles of unbroken concrete. They accepted the penalty of high drag to guarantee short-field performance. They accepted the punishing weight of the tail turret to give a slow bomber a chance to survive. They accepted the penalty of massive tires and pneumatic systems to ensure the aircraft could operate from the absolute worst environments imaginable. The Beagle was built for the end of the world. It assumed the infrastructure would fail, the supply chains would break, and the weather would be terrible. It traded elegance for resilience. It is a flying testament to the philosophy that in military hardware, absolute ruggedness has a quality all its own, allowing a design forged in the desperate years following World War II to cast a shadow over battlefields for more than half a century. If you like this deep dive, leaving a like helps get it out to other military history fans. Thanks for being here.